Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will continue our discussion on the small signal analysis of the BJT. So in the previous video, we have seen the general steps for the small signal analysis of the BJT circuit, and then we did the small signal analysis of the common emitter fixed bias and the voltage divider bias circuits. Now so far during the small signal analysis, either there was a no emitter resistor in the BJT circuit or it acted as a short circuit during the AC analysis. For example, in the fixed bias circuit, there wasn't any emitter resistor, while in the voltage divider biasing circuit, there was a bypass capacitor in parallel with the emitter resistor. So because of this bypass capacitor during the AC analysis, this emitter resistor acted as a short circuit. But if there is a no bypass capacitor in the circuit, then the AC analysis as well as the expression of the voltage gain and the input impedance will change quite a bit. So when this bypass capacitor is not used, then let us see the effect of this emitter resistor on the small signal analysis. And first of all, let us do the small signal analysis of the fixed bias circuit which is used with the emitter resistor. Now for the small signal analysis, we will follow the same steps. That means we will consider all the DC sources in the circuit as 0, while we will replace the coupling capacitors by the short circuit. And then after, we will replace the BJT by the small signal model. Now here if you see, then this emitter resistor is connected between the emitter and the ground terminal. So in the AC equivalent circuit, it can be represented like this. Also if you see over here, then this base resistor is connected between the base and the ground terminal, while this collector resistor is connected between the collector and the ground terminal. And this input signal is applied between the base and the ground terminal. So this is the AC equivalent circuit, and using this circuit, let us find out the voltage gain, the input impedance and the output impedance of the given circuit. And first of all, let us find out the voltage gain. So let's say the current which is flowing through this resistor RC is equal to I0. So if we apply the KCL at this node, then we can say that this collector current IC is equal to I0. So here this collector current IC is equal to GM times V pi, while this output current can be given as minus V0 divided by RC, where V0 is the output voltage. So from this we can say that this output voltage is equal to minus Gm times V pi times RC. So here we need to find the expression of the voltage V pi in terms of the input voltage. So here if you see, the voltage between these two nodes is equal to V in, right? So if we apply the KVL equation in this loop, then we can say that this input voltage V in is equal to V pi plus VE, where V is the voltage across this resistor RE. Now here, the current which is entering this base terminal is equal to IB, while the current which is flowing through this resistor RE is equal to I. And of course, this current is equal to IC. So from this we can say that this input voltage V in is equal to V pi plus IE times RE. That is equal to V pi plus IB plus IC times RE. Now here this base current is flowing through the resistor R pi. So we can say that this voltage V pi is equal to IB times R pi, or we can say that this current IB is equal to V pi divided by R pi, right? And this collector current IC is equal to Gm times V pi. So from this we can say that this input voltage V in is equal to V pi plus V pi divided by R pi plus Gm times V pi times RE. That means V in is equal to V pi times 1 plus 1 divided by R pi plus Gm times RE. Now here the R pi can be given as beta divided by Gm, right? That means 1 divided by R pi is equal to Gm divided by beta, and definitely it will be less than Gm because the value of beta is usually very high. So from this we can say that this 1 divided by R pi is much less than Gm. That means we can neglect this term. So from this we can say that this input voltage Vin is equal to V pi times 1 plus Gm times Re. Or we can say that this voltage V pi is equal to Vin divided by 1 plus Gm times Re. So now let us put the value of V pi into this expression. That means V out is equal to minus Gm times V pi times Rc. Or we can say that it is equal to minus Gm times Rc times Vin divided by 1 plus Gm times Re. That means the voltage gain V out divided by Vin is equal to minus Gm times Rc divided by 1 plus Gm times Re. So in this way, we got the expression of the voltage gain for the given circuit. Now here, this negative sign indicates that there is a phase difference of 180 degree between the input and the output signal. But more importantly, if you see, due to this emitter resistor, now the gain is reduced by the factor of 1 plus Gm times Re. Because if you consider the fixed bias case, then for that the voltage gain was minus Gm times Rc. That means now the gain is reduced by the factor of 1 plus Gm times Re. So similarly, now let us find the expression of the input impedance. Now the input impedance is the equivalent impedance of the circuit which is seen through the input side. And to find that, first of all let us find the equivalent impedance of the circuit which is seen just before this resistor Rb. Let's say this impedance is equal to Zb. Now here the voltage at this node is equal to Vb, and as you can see this Vb is equal to input voltage, right? While the current which is flowing through this terminal is equal to Ib. And as we have seen, this current is equal to Ic, while the current which is flowing through the resistor Re is equal to Ie. So if we apply the KVL in this particular loop, then we can say that the base voltage Vb is equal to V pi plus Ve. That is equal to Ib times R pi plus Ie times Re. Now we know that this emitter current Ie can be given as Ib plus Ic. That is equal to beta plus 1 times Ib. So from this we can say that this base voltage is equal to Ib times R pi plus Ib times beta plus 1 times Re. That means Vb divided by Ib is equal to R pi plus beta plus 1 times Re. And the ratio of this Vb divided by Ib is equal to Zb. That means Zb is equal to R pi plus beta plus 1 times Re. So in this way, we got the expression of the Zb. Now usually the value of beta is very high. So approximately we can say that this beta plus 1 is equal to beta. That means Zb is equal to R pi plus beta times Re. Now we know that this R pi can be given as beta divided by Gm. That means beta is equal to R pi times Gm. So from this we can say that this Zb is equal to R pi plus Gm times R pi times Re. That means Zb is equal to R pi times 1 plus Gm times Re. So this is the equivalent impedance which is seen through just before this resistor Rb. So now if we see the equivalent circuit, then it will look like this. That means now the equivalent impedance which is seen through the input side is the parallel combination of this RB and the ZB. That means Zin is equal to RB parallel ZB, where ZB is equal to R pi times 1 plus Gm times Re. Now if this base resistor RB is much greater than ZB, in that case we can say that the input impedance is approximately equal to ZB. So this is the expression of the input impedance, and as you can see, because of this emitter resistor, now the input impedance will increase. So similarly, now let us find out the output impedance. So the output impedance is the Thevenin's equivalent impedance which is seen through the output side, and for that we will consider all the independent sources in the circuit as 0. That means while finding this output impedance, we will consider the input voltage source as 0. That means this voltage Vin will act as a short circuit, and due to that this resistor RB will also get short circuited. And once the input voltage is 0, then this voltage V pi will also become 0. So let us see how it is. So if we apply the KVL equation in this loop, then we can say that voltage V pi plus voltage VE is equal to 0, where VE is the voltage across this resistor Re. That is equal to V pi plus IE times Re, that is equal to 0. Or we can say that it is equal to V pi plus IB plus IC times Re, that is equal to 0. Now we know that this IB is equal to V pi divided by R pi, while this IC is equal to Gm times V pi. So from this we can say that it is equal to V pi plus V pi divided by R pi plus Gm times V pi times Re is equal to 0. And from this we can say that this voltage V pi is equal to 0. So once this voltage V pi is 0, then this current source will also become 0, or we can say that it will act as an open circuit. So now if we see the Thevenin's equivalent resistance which is seen through the output side, then it is equal to RC, or we can say that the output impedance is equal to RC. So in this way we got the expressions of the input and the output impedance as well as the voltage gain for this fixed bias configuration which is used with the emitter resistor. And similarly, we can find the expressions of this voltage divider bias circuit when the emitter resistor is not bypassed with the bypass capacitor. So now to find the AC equivalent circuit, we will follow the same procedure. That means we will consider all the DC sources in the circuit as 0, while we will replace the coupling capacitors by the short circuit. And after that, we will replace the BJT by the small signal model. So if we rearrange this circuit, then it will look like this. That means here, this emitter resistor is connected between the emitter and the ground terminal, while the resistor R1 and R2 are connected between the base and the ground terminal. Similarly, the input voltage also is connected between the base and the ground terminal. While on the output side, this resistor RC is connected between the collector and the ground terminal. So here, the expression of the output impedance and the voltage gain will remain same as the previous case. That means here, the output impedance is equal to RC, while the voltage gain is equal to minus Gm times RC divided by 1 plus Gm times Re. But now, the expression of the input impedance will slightly get modified. So now the input impedance is the parallel combination of R1, R2 and the ZB, where ZB can be given as R pi times 1 plus Gm times Re. Alright, so from these expressions we can say that without the bypass capacitor, the voltage gain will reduce while the input impedance will increase. And for the better understanding, let us take one example. So in this example, we have been asked to find the voltage gain, the input and the output impedance for the two cases. In the first case, when there is a bypass capacitor of 10 microfarad and in the second case when there is a no bypass capacitor. So in both cases, we will be required to find the value of the transconductance. And for that, first of all, let us find the value of the DC collector current. So to find the value of the DC collector current, or for the DC analysis, let us consider all the AC sources in the circuit as 0, and let us consider all the coupling and the bypass capacitors as a open circuit. So if we see the equivalent circuit, then it will look like this. So now to find the DC collector current, let us apply the KVL equation on the input side. So applying the KVL equation, we can write 20 volt minus IB times 470 kilo ohm minus VBE minus VE, that is equal to 0. Now here let us assume that the value of voltage VBE is equal to 0.7. That means 20 minus 0.7 is equal to IB times 470 kilo ohm plus IE times RE. Now we know that this ammeter current can be given as beta plus 1 times IB. That means 20 minus 0.7 is equal to IB times 470 kilo ohm plus beta plus 1 times IB times 0.56 kilo ohm. That means IB is equal to 20 minus 0.7 divided by 470 kilo ohm plus beta plus 1 times 0.56 kilo ohm. Now here the value of beta is equal to 120, and if you put the value of beta in this expression, then the value of the base current IB will come out as 35.89 microampere, or we can say that it is equal to 35.9 microampere. So from this we can say that the collector current IC is equal to beta times IB, that is equal to 120 times 35.9 microampere. That means the collector current IC is equal to 4.3 milliampere. So the transconductance GM can be given as GM is equal to IC divided by VT, that is equal to 4.3 milliampere divided by 26 millivolt, that is equal to 0.165 Siemens. So in this way we got the value of the transconductance. Alright, so now let's do the DC analysis of the circuit when there is a bypass capacitor. So in that case, if we see the equivalent circuit, then it will look like this. So previously we have already seen that how to get this equivalent circuit, right? So in this AC equivalent circuit, the input impedance can be given as 470 kilo ohm in parallel with R pi. Now here this R pi is equal to beta divided by GM, that is equal to 120 divided by 0.165, and if you calculate it, then this R pi will come out as 727 ohm. That means the input impedance is equal to parallel combination of 470 and the 727 ohm, that is equal to 725 ohm. That means the input impedance of this circuit is equal to 725 ohm, while the output impedance Z0 is equal to RC. That means in this case it is equal to 2.2 kilo ohm. And if we see the voltage gain, then the voltage gain can be given as minus GM times RC, that is equal to minus 0.165 times 2.2 kilo ohm, that is equal to minus 363. So as you can see, with this bypass capacitor, the voltage gain is high while the input impedance is low. So similarly, now let us find out these three parameters when there is a no bypass capacitor. So without this bypass capacitor, if we see the AC equivalent circuit, then it will look like this. And for this circuit, first of all let us find the input impedance. So as we have seen, the input impedance can be given as RB parallel ZB. So here this RB is equal to 470 kilo ohm, while the ZB can be given as R pi times 1 plus Gm times Ra. Now we already know the value of the R pi, that is equal to 727 ohm, right? So from this we can say that the ZB is equal to 727 times 1 plus 0.165 times 560 ohm. And if you calculate the value, then this ZB will come out as 67.9 kilo ohm. That means the input impedance Zin is equal to 470 kilo ohm in parallel with 67.9 kilo ohm. That is equal to 59.3 kilo ohm. So as you can see, without this bypass capacitor, there is a significant increase in the input impedance. Now in this case, the output impedance will remain the same. That means the output impedance is equal to RC, that is equal to 2.2 kilo ohm. But now let us find out what will be the voltage gain. So the voltage gain can be given as minus GMRC divided by 1 plus Gm times Re, that is equal to minus 0.165 times 2.2 kilo ohm divided by 1 plus 0.165 times 0.56 kilo ohm. And if you calculate the value, then this voltage gain will come out as minus 3.88. So as you can see, there is a significant reduction in the voltage gain. So when this bypass capacitor is not used, then there will be a significant reduction in the voltage gain. Now from the AC point of view, this circuit with the bypass capacitor and this second circuit without the emitter resistor will provide the same gain. But with the DC analysis perspective, this emitter resistor provides the better biasing stability. And in fact, we have already seen this during the DC biasing of the transistor. So by using this bypass capacitor along with this emitter resistor, not only we can improve the DC biasing stability, but we can also improve the voltage gain of the amplifier. So I hope in this video you understood the effect of the bypass capacitor on the amplifier circuit. That means with and without bypass capacitor, how the performance of the amplifier circuit will change. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.